Hello dear students, welcome to mathematics class. In this class let us discuss the theorems on group theory. So here this is the first theorem of this class. Now prove that a group G is abelian if B inverse into A inverse into B into A is equal to E, where E is the identity element of G for all A comma B belongs to G. So here the given condition is B inverse into A inverse into B into A is equal to the identity element. So if this condition is true in a group G, then that G is the abelian. So that is the meaning of this theorem. So here first we need to consider G as a group, means that is already satisfying the four properties: closure, associative, identity and inverse. That is a group. Now along with that, if it satisfied this condition or this condition is true in a group G, then that will be abelian. So already for abelian group, the condition we need to satisfy is A star B is equal to B star A or AB is equal to BA. This is the condition what we need to show. So therefore here let G is a group. Let us consider G as a group. Now here the given condition we have the condition is B inverse into A inverse into B into A is equal to E. So it is the given condition. By using this condition we need to prove that AB is equal to BA. If we prove this condition, then it is enough to say that G is an abelian group. So therefore now it is the given condition. Now pre-multiply by B on both sides of the above expression. Now pre-multiply by B. Pre-multiplication means we need to multiply the element B on the left sides of the expressions B inverse, A inverse, BA and E. So therefore if we multiply this one by B, then it becomes B inverse, A inverse, BA is equal to BE. Right? Now B into E is equal to what? This one is B only. This is by using the identity law, because in identity law we said that A star A is equal to E star A is equal to what? A itself. So therefore here we are multiplying B by the identity element E, means the element B itself. So now on LHS we have B and B inverse. By using the inverse property, what is that inverse property? A star A inverse equal to A inverse star A is equal to E, right? So here we have B and B inverse. So means the product of these two will be is equal to what? E. Now A inverse as it is, B as it is, A as it is. Only we have changed B inverse as the identity element E. Now multiply this E to whole element, then there will be no change in the element A inverse BA, right? So therefore A inverse BA as it is, and this is equal to what? B only. And now here we have BA and we need to prove that BA is equal to AB. So here already B is there. On the left of B we should put A, means whenever we are multiplying left sides of the elements, then that is called as pre-multiplication. Now pre-multiply by A on both sides. Now we need to pre-multiply the element A. So then it becomes A inverse BA is equal to AB, right? Because we are pre-multiplying A, so therefore that becomes A inverse BA is equal to AB. And now A into A inverse, that is the identity element E. So here we can write by using the inverse law, we can write A inverse into A as E, and then BA as it is, and here AB as it is. Now multiply BA with the identity element E, then that becomes E into BA, that is nothing but BA only, which is equal to AB, right. So therefore BA is equal to AB, so it implies that commutative property satisfied, right, because AB is equal to BA or BA is equal to AB, both are same. If that condition is true, then we can say that commutative property is satisfied. If commutative property is satisfied, then it implies that the group G is an abelian group, right. So therefore if the condition that B inverse A inverse BA is equal to the identity element E, then G will be the abelian group. Means if this condition is true, then that is nothing but AB is equal to BA, because indirectly we are proving that AB is equal to BA, means the commutative property is satisfying. So therefore they have given this is given condition, which is the condition for a commutative group, because by using this condition we have proved that the group G is abelian. So therefore it is the proof for the given theorem, and already we have proved that G is the abelian group under the given condition. The next theorem is prove that the inverse of an element in a group is the element itself. So here inverse of an element in a group is the element itself. Symbolically we have written this as inverse of A inverse is equal to A itself. So it is the meaning of the theorem, and it is true for each and every element of the group G. So means you can write B inverse whole inverse, that is equal to B itself, like that. Means if A is the element of the group G, means here first of all G must be a group, means that has to satisfy the 4 laws closure associative identity inverse, that is fixed. Then inverse of A inverse is equal to A. Now let us prove this one. Before proving this theorem, let us discuss the statement of inverse law. What is the statement? Here let us write the statement of the inverse law. Here for all A belongs to G, right, there exists A inverse belongs to G such that A star A inverse equal to A inverse star A is equal to E. Means that A inverse, it may be post multiplied or pre multiplied to the given element, the result must be equal to the identity element. Here we are operating that on the right side of A, that is nothing but post multiplication, and here left side of A, that is the pre multiplication. So therefore independent of the position of A inverse, the result of that must be is equal to what? The identity element. So it is the statement for inverse law. Now let G be a group, let G be a group, and now let A belongs to G. Since A is the element of G and G is a group, then we can write that A inverse belongs to G, because inverse law satisfied for G. Inverse law means for each and every element there is a unique inverse for them. So therefore since A is the element of G, then it has to possess the inverse. So its inverse is given by the element A inverse, which is also in G. Now by using this condition A star A inverse, we can write that here we have written this for A, And now let us write the same condition for A inverse, means in place of A, let us substitute A inverse. So then that becomes A inverse into A inverse whole inverse. Here in this A star A inverse is there, instead of star we are writing dot or multiplication directly. Here A is equal to A inverse, again A is equal to A inverse, this inverse as it is, so therefore that is the whole inverse. Now therefore A inverse into A inverse whole inverse is equal to the identity element E. And now this identity element can be written as A inverse into A, because G is a group and E is the identity element of G. Now here A is the element and A inverse is the inverse of A. Now if you multiply A inverse and A, the product must be equal to what? Identity element. Here it is the statement A star A inverse equal to E, or A inverse star A is equal to E. So therefore here we have written that E is equal to A inverse A. Now A inverse into A inverse whole inverse equal to A inverse A. By equality we have written this expression. Now by using the left cancellation law, means on the left of A we have A inverse, and on the left of this element we have A inverse, means we can cancel out this A inverse and this A inverse. Then remaining A inverse whole inverse is equal to A. Now here this is by using left cancellation law. And here we proved this by using the condition A star A inverse, right? A star A inverse, we have proved that A inverse whole inverse is equal to A. And similarly we need to prove by using the second condition that A inverse star A is equal to A, that by using the second condition, and in place of A again we need to substitute A inverse only. So therefore now A inverse whole inverse is into A inverse. A inverse whole inverse into A. Here we are considering this element on the left side of A inverse. E is equal to the identity element E, and this is equal to nothing but A into A inverse, because A star A inverse equal to E. Now this one is A inverse whole inverse, and here it is A inverse is equal to A into A inverse. Now this A inverse is on the right side of A and as well as right side of this element inverse of A inverse. So therefore we can cancel out these two elements, then remaining A inverse whole inverse is equal to A. This is by using the right cancellation law, because here A inverse is on the right side. If the element is on the right side, then we need to use the right cancellation law. So therefore it implies that by using these two conditions we can say that inverse of A inverse is equal to A itself. So therefore this is the proof of the theorem, that is inverse of the inverse of an element in a group is element itself.